Hey folks, Dan here. Today on the Microarch Club podcast, I am joined by Robert Garner. Robert has had a long and impactful career working at many influential companies, including Xerox STAR, Sun Microsystems, IBM, and others. At each of these stops, he has contributed and in many cases led the development of computer software and hardware systems that shape the industry today. One of my favorite parts of interviewing Robert is the stories that he shares about working with a star-studded cast of colleagues and how they worked together to design and build machines that were often well ahead of their time. As with most episodes, we start with Robert's upbringing and exposure to computing before jumping into his career and the products he worked on, spending the majority of our time discussing his work on the Xerox STAR Dandelion hardware and his experience leading the definition of Sun Microsystems SPARC instruction set architecture. We round out our discussion with the restoration work Robert does today at the Computer History Museum and his upcoming book on the history of Ethernet. This was an incredibly enlightening conversation, and I want to thank Tom Lyon, who initially introduced me to Robert and has served as an incredible resource for computing history through his social media accounts and appearances on the Oxide and Friends podcast. With that, let's get into the conversation. All right, Robert, welcome to the show, and thanks for joining me.
No, thank you.
Well, it's an honor to have you here. I wanted to give a little bit of background on how we got connected, because I always like to shout out folks who help me meet other people who have interesting backgrounds and stories and histories. And I had reached out to Tom Lyon, who I believe you worked with at Sun, and I was asking Tom some questions about an Oxide and Friends podcast episode where they had kind of talked about the history of SPARC, and I had written some about register windows, which we'll get into later. And Tom said, you need to meet Robert, and connected us. And since you've shared a lot of awesome information with me, so shout out to Tom, but I'm super glad to have you here, and I think we're going to be able to cover a lot.
No, it's great to be on your podcast.
Awesome. Well, let's jump right into it. Obviously, there's a number of things at Xerox and at Sun that we want to talk about, but I always like to learn a little bit about folks' background, because I think that kind of influences where you end up later on. So what is kind of your upbringing, and what kind of led you to get into processor design and computers in general?
Yeah, that's a way back question. Yeah, so as a younger person, I was interested in two things: natural history, the outdoors. We had a cabin in the mountains in Arizona where I grew up, but also in electronics. As a kid, popular electronics gave you the belief you could just build anything, just get a few components. Of course, I couldn't afford them, but so I would devour all the issues of each issue of popular electronics and just hope that the components would come raining into my house somehow.
Right.
If anyone offered free components, that was a heyday. My mother would, on her way into town, this is in Phoenix, Arizona, I would say, please drop me off at a library, and I would consume, the books on physics and engineering there. I was, I guess you'd call a young geek.
Nice. Well, what kind of age did you start to actually get exposed to, physical machines, and maybe start to write some code and that sort of thing?
Yeah, well, that happened pretty young. I think in this category, when I was in grade school, I think 7th or 8th grade,
wow.
I learned that some friends of my parents had access to a computer. So I said, well, if I write a program, will you run it for me?
Right.
So I think I wrote a little tic-tac-toe program, and they would go run it for me, and it probably wasn't probably it wasn't as good as Bill Gates's program I've read, but I had the sense that I could get access to real computers, and that was very exciting. Very exciting.
What was the programming model? Was that on punch cards, or were you?
No, to be honest, I don't know what the adult did, but he probably had to put it on punch cards.
Right.
It was a GE 225 or
Okay.
425 mainframe, the same computer that was being offered in time-sharing systems and was abysmally slow as a time-sharing system. But I probably wrote it in Fortran or something.
Right. Right. And as you kind of got up into higher levels in high school and that sort of thing, did your schools have any access to time sharing systems or anything like that?
They did. We were very lucky. One thing to keep in mind is post Sputnik, pretty scary when this little thing goes around in the sky for the first time.
Right.
There was a lot of funding for science and technology in American high schools, and including in Arizona. I in high school, so we had a fantastic mathematics teachers. We had so we had access. We had a time sharing system that had access to a scientific data system, Sigma 7 computer. We could bang away on that teletype anytime we wanted to, although we learned that if you actually went to where it was, in a building downtown, they would let you have access to it at night. If no one was logged in, they let us have the whole $20 million computer, which was really cool. So we would run our little dumb programs until someone logged in, let's say at 1 a.m. or 2 a.m. So that was great fun.
Right. And were you mostly at that point in time programming computers exclusively, or were you also getting into, building them and continuing with your electronics tinkering?
Well, that's an interesting question. One thing that happened when I was in high school is I would visit Arizona State University Library.
Okay.
And I would sneak in on a Friday night. No one noticed I wasn't a student, I guess. And I would just walk the show. I knew where, the codes were for the books on computers, and I would find the books on computer design. And you'd look at them and go, oh, this is okay, this is pretty straightforward. And I thought, well, do I really want to build my own little computer? Some friends would do that, like for science fair projects, and they just seemed so wimpy. It was like, well, why would I spend my time doing that if I can get access to the real enchilada? So I in high school, as in any time, you focus on what's right in front of you. In the social scene,
right?
And we actually had a fantastic, like I mentioned, a mathematics professor. Several of us actually scored 4th place in the nation on the national math exam.
Wow!
And the school right above us was a place called Palo Alto High School, which we'd never heard of in California. So high school was just a great. I mentioned I was into natural history, so I actually founded the Saguaro High Conservation and Ecology Club, which was the first ecology club advocate in the state.
Oh, wow.
We set up the first recycling center in Scottsdale, Arizona in the late 1960s. So very busy at that time.
Right. That sounds like quite a lot for a high school student, but afterwards you went on to go to undergrad at Arizona State. Is that right?
Yes, I had some friends. We had a science club, several of us, and one of my friends in that club. And we'd build 3D chess sets like there were in Star Trek. And
right.
Build tube amplifiers. He got a job with a math professor there, and I joined him, who was doing 3D surface illustration. It was on a Tektronix 4010 storage screen. And we would write the code on a PDP-10 time-sharing system, and the bits would come over the 300 bit per second, 300 baud phone line and display on the screen. I realized we could record on a reel-to-reel tape recorder at a slow speed and then, replay it back at a higher speed to get faster graphics.
Right.
I wrote a little hidden line removal algorithm, which wasn't that great, but it worked on simple surfaces. And I also had a job with that was with Greg Nielsen. I also had a job with Dr. Barry Lesowitz in the psychology department, where he had a PDP-15, an 18-bit computer with D to A's, and they would send audio signals into soundproof booths and torture the students.
Right.
How can you tell where something is by just listening to the sounds? And we did a lot of assembly language programming there. The PDP-10 gave me experience in assembly language programming for the 10. So if the courses were boring, I had two great jobs as an undergrad and a place in the math department where I could hang out.
Right.
So it was just wonderful. I really appreciate Arizona State for doing that.
Absolutely. And so were you studying math, or were you studying computer science?
I was in engineering, and electrical engineering, although ASU had a broad curriculum in engineering. You had to take mechanical engineering. There was even still a slide rule class at the time. HP 35 calculator had just come out. We're like, whoa, wait a minute. But exposing us to mechanical stuff really helped later in my career, because you have to package, the electronic components. You have to package them. And, so you have to be able to communicate and understand what the mechanical guys are doing. So in retrospect, I wasn't as bitter about it later. They also let me take math classes in the math department instead of in the E department, and they would count as for my engineering degree. So they were really flexible. I really appreciated that.
Yeah, that's really interesting. I personally had a very theoretical computer science education, which at the time I enjoyed quite a bit. And I think, in my short experience of kind of like the academic system, it seems like, over the last few decades, there's been more of a rise in the theoretical computer science. And a lot of people really enjoyed that at the university I went to. But I definitely, looking back, wish I had had more of that holistic engineering experience and a little more, hardware and perhaps mechanical engineering perspective as well. And that's something I kind of I hear a lot from folks that maybe worked kind of like in the early semiconductor industry and that sort of thing, that they had more of this holistic view of the computer. And, perhaps the rising complexity in computing is one reason why it feels more specialized now. But that seems like a trend that I hear from folks.
Yeah.
And then after Arizona State, you went to grad school. What was that decision like, and how did you pick Stanford, and what was being there like?
Well, I really knew to get a really exciting and challenging employment, you really had to get a graduate degree. So I applied to many universities, and Stanford accepted me. And hey, California, and from Arizona, that's a shining thing on the hill across the horizon. Right. So I bid on that one. It turns out my father grew up in the Bay Area, so that was kind of a nice connection later on.
Okay.
I actually applied there. You mentioned theoretical. I actually applied for the information theory curriculum. I was really into information theory in college as well, in addition to taking all these practical engineering classes, and they accepted me there. When I came in, I was Marty Hellman and all these guys, and I was like, this is really intense just for a one-year master's program. So I asked if I could switch to computer engineering, and they said yes. So that was great.
So the program was still just 1 year though?
Really nice. The master's program is just 1 year, which is really fantastic because I really wanted to get out. I wanted to get out working for someplace. I took a lot of lab classes in that year, and labs are very intensive time-wise. So I was pretty overwhelmed. And I took Russian language again. I took Russian language in high school. That probably wasn't the greatest idea because that was pretty intense. And once I signed up for Don Knuth's algorithm class. And after the first 2 weeks, it's like the assignments were impossible, and it seemed like it was two classes in one. So I dropped it. And a few years ago, Professor Don Knuth is very active at the Computer History Museum. I had dinner with him. I said, Don, I took your class as a young kid, and I felt it was two classes in one. He said, oh, that's great, because that's the way I constructed it. I go, oh, I was so overloaded. If I had more time, I could have stuck with it. But I loved his Art of Computer Programming textbooks. Many kids today, I'm sure, are not exposed to it. And a lot of people don't even know who he is, but he's just a marvelous person.
Absolutely. Well, if it's any signal, I definitely know who he is, and I think folks in my program at least also were certainly exposed to him. So
they published all his articles in books, and one of the books is on his humorous articles, the ones that are all just jokes and fun.
Oh, nice.
Analyzing all the possible vanity license plates you could put together, and he discovered. So he has a great sense of humor, which is just remarkable.
Absolutely. Well, I'm sure once we get towards the end of the podcast, we'll touch a little more on your work at the Computer History Museum, which I think folks will find really interesting. But, you mentioned you're excited to kind of get into industry and get out of grad school. You ended up landing at Xerox. What was the process like getting there? And obviously, around that time, a lot of really important technology came out of there that has led to many of the products and things we have today. What was it like kind of getting into Xerox at that time?
Well, I think we were vaguely aware of PARC, but for me, it was dumb luck. I went to an on-campus interview. Employers would come in and interview you, and Bob Metcalf,
Oh, wow.
basically inventor of the Ethernet, was interviewing me. And it sounded exciting. The kind of stuff he wanted me to come work on there, I'll never forget. He called me I was staying in someone's garage. There wasn't great student housing at Stanford at the time, and he called me like at 11 or 12 o'clock at night. That was probably halfway through his workday. PARC was like a startup company.
Right.
And he said, "Well, do you want to try to do something besides all that easy coursework?" I'm like, "Easy coursework." Anyways, I knew he had a sense of humor. And,
right.
He was the most amazing as a first manager. That was his first management job, actually, as well. But so as his first management job and my first manager, it was a pretty special experience. He's a remarkable person. He really cares about people and opens his heart and speaks what's on his mind. Great person.
That's awesome. So you join Xerox, and you're coming onto his team, right? And what was kind of the first thing you worked on when joining?
Yeah, this was 1976. Well, first of all, I'll never forget during the on-campus interview, he showed me this thing called the Alto. I have one sitting next to me on the right here, and it had a bitmap screen, so you could do graphics, and it also had this 3 megabit Ethernet, and you could send a file or a whole disk pack between two machines in what seemed to be almost instantaneous. That impressed me, not so much the bitmap screen. But he hired me to help commercialize the 3 megabit Ethernet, which he and David Boggs had developed at PARC. By that time, there were probably 50 to 100 Altos working on a 3 megabit Ethernet. They had developed the first protocols. The email systems were coming up. There was a file server on the master time-sharing computer called Max. It was like being in heaven. Now I technically was in what was called the System Development Division, which was set up to productize the Alto. But we were co-located with the people at PARC, so I got to know all the people as if I was working there. Butler Lamson. So I started working with Chuck Thacker. I basically, what do we do next? And Bob actually set up as a goal to try to run at 20 megabits per second, which seemed a little aggressive.
Right.
We ended up running at 10. And we had analog people in the group. There was about 4 of us in the group that were going to design the entire workstation. What was called the Xerox STAR 8010 professional workstation, and I started the first Ethernet I did was called the Xerox Dolphin, or D0, which was meant to be the productized version of the Alto.
Right.
And as a kid out of school, I learned rather quickly that Chuck Thacker, who's equal to about 10 normal people, he was just remarkably brilliant. He could design something in 1 minute that would take you half an hour.
Yeah.
He wrote his own schematic editor. He pulled this system together, and it was like 3 times as complex as the Alto, what I would call the second system syndrome. But my first job was to build an Ethernet controller for that system.
And so you mentioned D0, and then there was a kind of a series of these D star processors, right? And
yeah.
There was D1, and then was Dandelion was the one that the Star workstation ended up being built on, right?
Yeah, the sequence was the Alto, the D0. The D1 was a slightly later machine. It was a pure Eckel.
Okay.
With ECL logic, extremely expensive and a lot of power. Like you didn't want to have one in your office.
Right.
It was probably like a 10 MIP machine. It's my watch today.
Right.
The Alto was probably a half MIP machine. The Dandelion, as you mentioned, that was the code name for the hardware that we designed. It was maybe a half a MIP machine, but it was faster than the Alto because it had a faster memory system. A huge difference between the Alto and the Dandelion was that in the Alto, Chuck had come up with a brilliant idea. I mean, it turned out on the TX1 back east, they had done this idea. But you have a bunch of hardware, and since hardware was, you're really trying to reduce the cost of the hardware. And so he basically came up with a multi-threaded idea to share the CPU, and the microstore memory with all the devices. So the Ethernet controller, the display controller, the disk controller, and low-speed I/O had microcode that did most of the work there. And the hardware was just small buffers, enough for a few words from the disk or a few words from the Ethernet. And the devices would, like on a normal bus, compete, priority order, compete for access to the CPU. And one of the challenges with that Alto design is that your microcode could keep control of the CPU as long as you wanted.
Right.
You had to relegate, you had to let someone else fight for control of the CPU. And that was an interesting experience for me, because I was writing the microcode for the mouse, for displaying the mouse on the screen at the time.
Oh, wow.
And it would stop working, and I would go look at the other microcode, and Chuck Thacker had spent too many cycles trying to get his microcode to work. So I said, Chuck, you're not giving me enough cycles just for the mouse to track. And so he'd go fix his, and then mine would work, and then he would go change his again, and mine would stop working.
Right.
So so Butler Lampson, who was the brilliant, savant at PARC, knew everything but operating systems and compilers and languages, and he got familiar with hardware there. He came up with a design called Wildflower. He actually wanted to have a design with like 0 chips in it, which, because he saw the D0 had gone one way, and let's try to make it even more focused.
Right.
And he had an idea where you should schedule fixed rounds for the microcode, so the display always knows when it's going to run. The Ethernet always knows when it's going to get a chance to access the CPU and main memory. Brilliant idea. Computers aren't generally designed that way. Usually it's a bus, and you, like I was saying, you ask for service, and if you don't get service, your buffer underruns or overruns.
Right.
And it's like, why do these computers work? I mean, they don't at a certain point. But this system, this idea, where there's guaranteed access to memory in the CPU on a regular basis, meant that if the processor met its cycle time, I/O would never get an underrun or overrun. So that concept that Butler came up with, we adopted that in the Dandelion. It basically followed the ideas that Butler had in the Wildflower, and we implemented that in the Dandelion. The Ethernet got 2 slots, the display got 1, the disk got 1, low-speed I/O, which is based on 8086, 8085. Kind of later took over the world.
Right.
So we knew, we designed the Dandelion, that if we met the cycle time goal, which was 137 nanoseconds, the fine structure of constant physics,
Right.
that it would work. And what a great project to work on.
Right. So if you're, the way I'm kind of like conceptualizing this is you're essentially like checking sort of like each slot each time through. Is there a performance penalty? Like, let's say you have a scenario where just one of those devices or peripherals or whatever you like to call it, one of those slots is the only thing that's active and doing anything. Are you paying a cost for kind of like checking or having each of them kind of occupy part of that loop there?
Well, if you don't have any I/O to move to or from memory, you don't ask for your slot.
Okay.
And then if no one takes that slot, it goes to the emulator, the language emulator.
Okay.
So in the case of the Alto, well, it's not slotted like this, but the language emulator was always lowest priority, so it ran the Nova instruction set, the Data General Nova instruction set. By the way, I have a Nova computer behind me there, you can see. That's from the soul of a new machine.
Right.
Novas were around PARC before they designed their Alto. And then they built a Smalltalk, the language Smalltalk that Alan Kay and his company designed, and Lisp. And so you could kind of tailor the CPU for the instruction set that you wanted. And for the Dandelion, we just did the emulator for the Mesa language, which was a language designed to Xerox SPARC. Didn't go anywhere after that, but it was the basis for all our machines. A very strong type checking language. kind of some aspects of object-oriented programming. Just a beautiful language, but it didn't have enough users to survive.
Right. Is the so looking at the kind of on PCB or the architecture, the chips on the board for the Dandelion, it was a bit slice architecture, right?
Yes, we won't be able to see it if you're listening to the podcast, but this is the actual CPU card.
Wow.
There are four AM2901, 4 bits each, so this is a 16-bit computer. And then the control store is at the bottom, 4K 48-bit words. And that is enough to cause a lot of trouble.
Right.
You could get, with a writable microcode, with a writable control store, what a field day for the language designers.
Right, right.
So they would run applications, representative applications, and re-encode the Mesa instruction set, the bytecodes, almost every week to see if they could get the code size smaller, because in the Dandelion we weren't sure if it'd go out with 128 kilobytes of memory, 384 kilobytes of memory, or maybe even 512 kilobytes of memory. And there was just so much functionality. It was a GUI.
Right.
There was email, there was networking, there was storage. It was remarkable how much functionality you could put into just half a megabyte of memory.
Right.
Just remarkable. Now it was all one unprotected address space. There was no user and kernel. But it was, so the classic CISC, complex instruction set computer,
right.
They could redesign it on a weekly basis and get the code size down. There was even one point where they implemented microcode swapping. You could swap microcode in and out of the microstore.
Wow. Wow.
Just kind of the pinnacle of CISC at the time.
Right. And so the reason why, kind of like looking back, the computers were designed in this way at this time, right, is because it was too expensive or not possible to have, a single integrated microprocessor, right? And so you mentioned the 2901, which I believe was kind of the control chip, and then there was all of these 2900 logic chips that you'd chain together depending on whatever the width of the logic that you were doing. Is that right?
Well, the 2901 was the ALU, so these are the ALU chips. Everything else is just decoding the instruction, the program counter, accessing the microstore, talking. This has the microtasking hardware so that the different microcode can run. So you have to save the PC for all the microtasks. That's basically about it. But fundamentally, we'll get to SPARC and RISC, but now's a good time as any, since we're talking about architecture. Fundamentally, the people at PARC were certainly aware of caches. IBM had implemented some caches on their very high-end 360s, the model 195. But caches would just add more cost.
Right.
Significant more cost. And without a cache, you're limited to main memory access, which is, in the case of the Dandelion, was 3 micro instructions. So during one of those slots I was telling you, where the microcode could get access to the CPU and memory, it could do one memory operation. Mm-hmm. So now you've got memory running 3 times slower than your basic instruction. Whereas in RISCs, you have single cycle, if possible, loads and stores, and that's because you have a cache. You can get to the cache typically in one cycle. And caches just were not in the cards at this time. And no one knew what the best instruction set looked like. So having a writable control store gave the flexibility to, especially as a research institution at PARC, to explore that. What are some... Of course, there are an infinite number of programming languages. So it would have taken the age of the universe to answer that question. But, as a research vehicle, it was a great thing. Now, as a product, it meant you could also, in the field, upgrade the microcode if you needed to. If there were bugs or you needed some new feature. There are some very complex instructions for process switching. So there were lightweight processes, and there was microcode for procedure calls, saving the arguments away and all that kind of stuff. It was a stack-based architecture, Mesa, unfortunately, and stack-based architectures have very slow execution times compared to others. In fact, Forrest Basket once came around with a little benchmark called Puzzle, and he ran it on our Dandelions, and it really sucked. We were like so slow. It's like these guys, developed this beautiful language, but no one had ever looked at how slow it was.
Right.
So I learned a lot of lessons there.
And when you say that there was no caches and it was stack based, so there's no registers or anything like that, right?
Yeah, there's just top of stack. Okay. And so typically, like in this design, it would be saved in a top of stack register on the processor card, and a little small stack. So there was a small area of registers in the hardware that I forgot to mention earlier.
Gotcha. And so how did you mentioned kind of like reprogramming the microcode in the field and that sort of thing. How did you actually program one of these machines?
That's a really good question. So these days we're so used to bits coming in over the network.
Right.
Well, okay. So during debug of the Dandelion, we set up an Alto with an umbilical cord talking to the I/O processor in the Dandelion, which could read and write the microstore, and could set breakpoints, so we could use that to debug. For the Alto itself, it was meant to be just a ROM-based microcode, but they added to it a writable microcode so they could access that through another Alto to read and write, or maybe through a Nova to read and write that. So that's how you could program the microcode. In terms of programming at the higher level, in the language and application layer,
right?
Typically, we do it via the Ethernet. So it's got an Ethernet, so we could boot from the Ethernet. You could load code from the Ethernet. Ethernet was so amazingly fast, 3 megabits per second. You've got a half MIP computer, but 3 megabits coming in. So it actually was too fast almost for the speed of the machines at that time. And then, of course, customers, it was floppy disks. I've got some 8-inch floppies around here somewhere.
Right. Is the I know Ethernet was obviously a big part of the story at Xerox and at PARC, and obviously has become a big part of the story everywhere. Was it kind of an instant success in terms of adoption, or was there a lot of work to make it become ubiquitous? What was it like around that time?
Yeah, that's something I'm investigating. As we'll talk about later, I'm doing a history of the Ethernet, and it was a struggle. I mean, back then there are so many ways you could pump bits over a cable. It wasn't wireless really at that point. I mean, Ethernet was inspired by the Alohanet at the University of Hawaii, but there were several other cable networks at the time, so you had to contend with, okay, I got mine, you got yours. What's the advantage, disadvantage? But the reality is Bob Metcalf and David Boggs made it work, and it worked. It just worked.
Right.
You put a cable. You just, I've got this is my hand here for those on the podcast. This is what the transceiver looked like. It's about the size of 2 cigarette packs, and you take your cable, which I have in my hand, and you put a tap on it, and first you put the tap on, then you actually screw this in and actually drill the hole by hand into the cable, and you took all the pieces out, and then you took the transceiver and you put it in like that, and then you put a transceiver, then you put a cable up to the transceiver. It goes to your Alto, which could be fairly long actually, 50 meters, and you were on the network. You could send email, and you could get onto the ARPANET,
right,
via the internet, and send messages to your buddies back east. Started out maybe as an option in 1973, but by 74, 75, by late 74, there were probably a dozen Altos working on it, and by 75 and 76, there were several dozen. And by the time I got there in 76, there were over 100. Wow. And then Xerox started setting up Ethernets in different sites, and they used the 50 kilobit lines that ARPANET was using and built gateways. They used the Novas, actually a little faster than this one, to be a gateway. So they actually set up the first internet most people don't consider the ARPANET an internet because, imps all talk to each other with a common protocol. But the first internet where you're going over somebody else's network to talk to another Ethernet somewhere else, they had, by the late 70s or early 80s, I mean, this will all be in my book, but they had over a dozen different sites fully, Ethernet fully at them interconnected via 50 kilobit lines.
Wow.
So Xerox was way ahead of its time, and people didn't realize how good it was.
Right, right. And I know that the Alto was built as, kind of a prototype machine, and there wasn't that many of them. But then y'all are tasked with building STAR and kind of making it, a commercial product. Was it successful as a commercial product, or how widely was it deployed?
Well, to be honest, at an engineering level, we thought it was successful because it did so much more than a mini computer of its time, right? So a VAX mini computer would be the size of a washing machine, and it didn't have a display, and the board to connect to Ethernet was 3 feet on the side, and it was 4 times as expensive. And because of Butler Lampson's idea and Chuck's idea of compressing the hardware, we were the cat's meow in terms of cost. It was extremely inexpensive and so powerful. It gave us all the paradigms we have today. Charles Simone wrote Bravo, the editor, which became Word when he went to Microsoft, a little unheard of program like that. Doug Bratz wrote an email program, which we're all familiar with. We didn't have browsers because there wasn't much on the internet at that point. I'll never forget the first person who tried to advertise something on the ARPANET. We were like, don't do that.
Right.
So, the Dandelion and the Xerox STAR, from our perspective, were very cost effective. But from a user perspective, they were too expensive. So the STAR went out at about $16,000.
Okay.
I'm sure we discounted it, but in today's dollars, that would be like $40,000.
Right.
And really, you needed more than just a workstation. You needed the file server, which was another Dandelion with a large disk, 80 megabyte disk. You needed a print server, and they had a low-end laser printer that printed beautiful documents, one every 5 seconds or 10 seconds or so, one page every 10 seconds. You needed a communication server, a gateway server to get to the ARPANET or to another site, another Ethernet site. Maybe that was optional, but you needed, in today's dollars, like $200,000 worth of equipment.
Right.
And most people at that time, the so-called information executives, whatever you want to call them, didn't know how to type.
Right.
And they had no idea what this weird thing is called a mouse.
Right.
That was a freaky thing. Xerox didn't know how to announce it. I'll never forget driving down Highway 280 and hearing my first ad for a mouse on the radio from Apple. I just about drove off the highway. A mouse on the radio. So they didn't know what why they needed it, and why would they spend that much money? I mean, their administrative assistants, their salaries were less than 100th the cost of this whole system. Mm-hmm. I could hire 100 secretaries.
Right.
And I don't know how to type. So, they only sold about 20,000 stars, I think, in the end, somewhere around there. I personally saw a large site at the NSA. They could afford it. They were very popular in Japan. It was the first kanji workstation there.
Oh, interesting.
Voice of America used them because it was multilingual. You could have different languages, fonts.
Right.
And that I remember reading one story about that where the person from some Slavic country, we won't mention which one, was afraid he was getting radiation from the monitor, and he refused to work on them because it was pretty scary.
Right.
So it was unfortunate that it's been penned as a failure, but 20,000 for a mini computer would be considered a success. So it just didn't have the, next was Apple's Lisa, which was $12,000 at the time, $24,000 to $30,000 today. Right. That was too expensive. Next was the Apple Macintosh, $5,000 then, $6,000 then. Maybe $12,000 to $15,000 today. I mean, would you spend $15,000 for a little thing, a little tiny screen with poor graphics?
Right.
So it took a while for the IBM PC was announced the same year and month as a Xerox STAR in 81. It was announced a few months later. And fine, it was inexpensive, but it set the whole world back from our perspective.
Mm.
It turned every male into an IT administrator. You're probably too young to remember the PC, but it had floppy disks and God knows, Charlie Chaplin were in all the ads that IBM ran, and everyone thought they needed one to be up with the world. And
Right.
it set the world back 20, 30 years in terms of an easy to use interface. I mean, the Xerox STAR designers, Charles Irby was one of the main people there, and I can't remember all the names. David Smith. By the way, there is the last demo of the Xerox STAR. You can see it online. We held it in 1998. I had two Dandelions working, and they were on stage.
Wow.
And they ran all the software, and you can see what that looks like online. But it was just too expensive, ahead of its time.
After that, I mean, I'm not familiar with many other machines that came out of, or many other computers that came out of Xerox. Was it just kind of determined that wasn't the path going forward? Like, why wasn't there more iteration since you felt strongly?
There actually
Okay.
was. Xerox gets blamed for not pursuing it, but they did. I mean, the next version was called Daybreak, the 8085. I had one here, but did I give it away? No, I still have it somewhere. So it was smaller, not instead of a foot and a half wide by 4 feet tall and 3 feet, no, not 4 feet, by 3 feet tall and 3 feet deep. It was more compact.
Okay.
Basically the same architecture, just compressed a little bit. But that, the PC was out. People were doing spreadsheets. Finally the STAR got a spreadsheet. That didn't sell that well. They then ported the user interface to a PC. I forgot what that was called, but that Global View or something, that sold. But now all of a sudden the data is incompatible with what everybody else is doing, right? It's not Microsoft Word and Excel and
Right.
PowerPoint, whatever, So it never. They tried. They put effort into it, but it never. Being first doesn't always mean you win.
Right. Absolutely. Well, you mentioned the mouse there, and maybe I'll use this to kind of wrap up your time at Xerox and PARC. I know you worked on it was the sensor chip, right, and the optical mouse. Is that right?
Yeah, when I was when I finished the Dandelion work and the Ethernet, I moved into Xerox PARC proper. I worked for Lynn Conway of the famous Meade Conway design method, her VLSI group. So I learned about chip development then. And Dick Lyon was there and had invented this amazing version of the mouse. Let's see, yeah, this is actually it right here. There's an optical sensor. I'm showing this to people on your blog, so you'll have to bear with me. But there were 3 lenses, and what Dick had done is he designed like a 6x6 array of sensors, and your mouse pad was equidistant spots. So a print pattern with equidistant spots, or maybe your blue jeans would work, and it would be like a neural net. It'd be cross coupled, so inhibitions and enhancements, and it was set up to try to recognize the dot pattern. So it would stabilize on a dot pattern, save it, stabilize on a new dot pattern, compare which way the dots had moved, and decide which way the mouse had moved. Brilliant design. And I basically came on after he had it working and worked with him to try to work out some bugs and stuff. But he was a very inspirational person to work with.
Right.
Amazing person.
You mentioned the Meade Conway and structured VLSI. That was a pretty big difference from the approach to designing the Dandelion, right? Where you had all of these individual chips. VLSI was now you were designing the chips yourself. Is that right?
That was the goal.
Right.
Lynn broke the barrier to people learning about how chips worked. I mean, we used to teasingly say, she came up with the idea that all you needed was a red, green, and blue pencils, and you could design any chip. Because, if the gate was one color green and poly was red, so you just crossed red with green, you got a transistor.
Right.
And I mean, it was a joke, right? But so it made it very accessible. And then we had the chip project, the Moses. They set up the whole procedure where you could create a layout, submit it, multiple little pieces of the chip. The chip would get fabricated, it would come back. I did a chip like that. It was a very simple chip. It was a serial adder. Jim Clark did a chip, the predecessor to the geometry engine, which, of course, he later became famous for other reasons. So I even later learned that people at Intel read the Meade Conway book because it was really educational for. Back then, you really had to lay out a chip by hand. The tools weren't ready yet. John Ousterhout was working on Magic CAD tools for chip design, but they weren't ready yet. So you were very limited what you could do. I actually hand designed a Mesa chip because I thought we need to get Mesa into a chip. Everyone knew this was coming. We needed to do it.
Right.
But it just wasn't coming fast enough. And when you get a catalog of chips, you can build something right away, TTL chips, whatever. But with the VLSI, you got to sit down, you got to lay. There was one guy at PARC, I'll never forget. I walked into his office. We worked, till 3 a.m. late at night, and he had a 2D chip editor up, Icarus, I think it was called. He was starting in this corner, heading for that corner. And I was like, that's no way to design a chip.
Right.
And they started a project at PARC called Dragon, which was going to be eight custom chips to do a multiprocessor with a amazing cache coherency protocol, memory coherency and cache coherency protocol. And I just knew they couldn't possibly accomplish that based on the set of the tools. And that was one of the reasons why I left and went to Sun Microsystems.
Right. So getting into Sun Microsystems there, I know you obviously were hugely influential in the SPARC instruction set architecture design. What was, coming into Sun, is that what you knew you were going to work on? Did they come in and get you to come work on that, or what was that process like?
Yeah, so there were some events that kicked it off. Xerox SPARC had an unfortunate thing where the lab director, Harold Hall, came down and kind of interfered with Bob Taylor, and much of the computer science lab actually revolted and left.
Oh, wow.
And formed a new lab at Digital Equipment Corporation, DEC System Research Center, SRC. And they kind of just shut down PARC as we knew it then. I mean, Alan Kay and SSL people still stayed for a while, but so it was time to look around. And Sun, to me, looked like just another Motorola 68000 based workstation company. I couldn't see why it would last any longer than anybody else. It was tiny. There were probably about 20 workstation startups at that point. And Dave Patterson, who was professor from Berkeley, who was consulting with the Smalltalk group, actually, he got roped into consulting at Sun. Bill Joy was in his classes. He'd always say how Bill talked more than he did. Bill talks faster than a racing airplane fighter. Bill had been famous for porting, for creating BSD Unix. Mm-hmm. And so Bill had attracted Dave Patterson to consult at Sun Microsystems, and Dave Patterson knew my positive background on the Dandelion and suggested I might join them. I was like, why? Well, one Friday night, my wife sent me to Tower Records. You remember Vinyl Records? Yep. We used to have to go to a store. There was no Amazon to walk around, maybe listen to them first, buy a record. My wife wanted a certain record, and in the store was there was that night, Friday night at Tower Records, where was Eric Schmidt and Bill Joy walking up and down the hallways, and they said, "We want you to come join us." And I go, "Why?" So they twisted my arm. We want to do a RISC, is what Bill said. I said, "That sounds cool." The Dandelion, it had 137 microsecond cycle time, but I needed 3 of those just to do one instruction, so why not do a RISC? And I thought that was a good idea. So my wife hadn't sent me there that night, I wouldn't have joined Sun probably.
Wow.
I don't know what I would have done instead. But when I started at Sun, though, I was surprised that it wasn't quite the way the ticket I had been sold. Bill said, well, my boss, Bernie LaCrue, who had been at DEC, Digital Equipment Corporation, he had managed the VAX system. He knew what a risk could be like.
Right.
Yeah, Patterson had written articles about how the VAX was too complex, and that's where the CISC term was coined. Bill said, well, Bernie has just asked us to do a floating point accelerator because Sun was last in the list. If you're an engineering company, why would you be last in the list in performance, right? So this has got to be fixed.
Right.
So Bill said, well, if I'm going to do a coprocessor, I might as well make it a RISC, the fastest processor. I said, Bill, I didn't join this company to do RISC as a coprocessor.
Right.
Come on, Bill. And, and it was a 68,000 based company. There wasn't NFS. There was no way to have different binaries on the network. And so Dave and I basically spent several months convincing Bill that we needed to do it as a coprocessor. And people like Dave Goldberg, who had been at DEC WRL, they had done a Titan Echo RISC machine there. He was like, you don't need a 68,000 in this anywhere. Just do it. And so finally, we convinced Bill to do it as the main processor. And at that point, Bill said, well, it's got to be open. And we're like, I don't care. Because he knew that Xerox had failed by keeping everything closed and proprietary.
Okay.
He was so familiar with the Xerox's experience.
Right.
And so he became, the cheerleader for SPARC, and supported it in a huge way after that.
And what was the process like of kicking off that effort and designing an instruction set? I know there was lots of inspiration from the RISC designs from Berkeley, but
Yes.
in some regards, starting from scratch with the new instruction set, how'd y'all begin and start to make decisions about trade-offs and that sort of thing?
Yeah, it was a very contentious process. I obviously Patterson, we knew all about RISC-1 and RISC-2.
Right.
And I basically, it is an open process. So I looked at all the risks I knew about. So the 801 had been relatively well written up in the literature. It wasn't that secret of a project. So I looked at the 801 instruction set. I looked at the Titan instruction set at DEC, which is a research lab as well. There were other risks. ARM was just starting at that time. Pyramid was doing something. We didn't know all the exact details. We knew HP was doing something, and we didn't know the details because they were all close-lipped about it, close-mouthed about it. But I looked at them all, and they fundamentally weren't that different. And since Patterson was there, and since RISC had been done in the open, no one could go after us for patents. So I said, let's just stick with the Berkeley RISC, but we need to add some things to it. We need to add floating point.
Mm-hmm.
We need to give it an MMU, a memory management unit of some sort.
Right.
We need to. A lot of people were doubting Patterson because, this is just a student project. It's not a real world thing. But we knew how to make it real world.
Right.
Dave was consulting there one day a week in my office for 4 or 5 years. Great person to have as a consultant. He was a very fatherly figure. He would break up fights, So it's very contentious because when you design an instruction set, you can put anything in it you want. And Bill wanted tags, so people could do a tagged architectures like in Lisp. We put in some tagged instructions. They were actually had a bug in them. So I guess our heart wasn't in them. I'll never forget going to Texas Instruments, and they just called me out there. I said, why do you want me to come? And I walk in the room, and there are all these dour faces. Like, you guys screwed up the tag dat instruction. I'm like, oh, shit. They roasted me.
Right.
So it took 2 instructions instead of 1 to do what you wanted. Like, oh, God.
Right.
So Bill was so... He was just like a fast deal maker. And he would say, all right, I'll stop asking for X if you X and Y if you do Z.
Right.
And he would just interrupt and I formed what's called an architecture committee. So the great thing about Sun is that we had system people and we had OS people. Sun OS was known already to be stable and reliable.
Mm-hmm.
We had compiler people. We actually had user interface people. We had system people. So I had all those people on the committee, and we together I ran that group, and we decided what to put in and what to take out. And Bill would interrupt. At one point, I actually shot him with a water pistol. I'll never forget. Bill, quiet. And I'd go to Bernie and say, Bernie would say, when can we get done defining the instruction set?
Right.
And I said, well, if you get this VP out of my office.
Right.
He was so into it, in retrospect, we loved it, but it was kind of disruptive. And the reality is, at the same time, we had no freaking idea how we were going to implement it.
Right.
Because we couldn't start just laying out rectangles on a chip starting on this corner going to that corner. We had no full custom. I mean, I had a little experience. We had no real full custom design experience. So we went out talking to chip firms to see who could do something for us. And most of them were based on standard cells, which are a great idea for doing general logic. I wish Xerox SPARC had done standard cells. They would have not fallen behind so far. But we couldn't find anything that would meet our speed targets. We know we had to go at least 16 megahertz. I know that sounds slow, but that was fast for the time. And the Meade-Conway design method couldn't achieve that either, because it wasn't designed for speed, really, past transistors and dynamic storage. And luckily, we hired this guy, Anand Agrawal, from STC, Storage Technology, and they were trying to build an IBM mainframe clone. And they had experience with Fujitsu, and Fujitsu was doing a gate array. And they just stepped up to a 20,000 gate array with a 4 kilobit memory and 1/4 of the die. That was just enough to do at risk. So as soon as we had Fujitsu in place, I could finalize on the instruction set, and we launched.
Right. And I know the first public, I guess, release of SPARC was V7, right? And so
Yes.
what were what happened to the previous versions before that?
They were my document version numbers. People normally do 0.1, 0.2. I said, what is this decimal crap? What's wrong with integers? So I guess the marketing people made it sound like, it was cool because but it was just the version numbers of my documents. Every month I would update the version number. That's pretty funny.
Yeah, fascinating.
There wasn't room in the gate array for multiplying, an integer multiply instruction.
I heard this, yeah.
But the risk mentality was that the compiler only really needed most of the time to just multiply by 2 or 4, to shift addresses. And so, just a shift and add is what we put in initially. For floating point, certainly there's no room for all the floating point. We knew we needed a floating point. So we had another whole gate array, the floating point control chip, which just controlled a Waytech 1164 and 1165. Waytech had just come out with a floating point multiplier and an ALU, which did add, conforming to the IEEE standard, single and double precision, 32-bit and 64-bit. One of the members of the architecture committee was David Huff, who worked for Professor Kahn, who, spearheaded the IEEE 754 floating point standard. And he strongly believed we needed extended precision.
Okay.
You have more than 64 bits, so that when people write their algorithms, if they're starting to accidentally underflow too much, they won't lose significant bits. They'll be held in that extended precision thing. And we're like, really? But he insisted so hard that we defined, and also because Motorola, they were designing their 68881 floating point coprocessor, and we knew they were going to do 80-bit. So I was like, we can't be worse than them,
right?
Can we? So we put 80-bit in the architecture, but we never ever implemented it in hardware. So it was always done in emulation. But that's the kind of thing that happens.
Right. Is the I know SPARC, stands for Scalable Processor Architecture. What was kind of the you're talking about optimizing?
Actually, if I can interrupt you, it actually didn't stand for that in the beginning.
Oh, really?
No. When we started the project, we said, we're going to have to name for this thing.
Right.
So Will Brown, who had done the instruction set simulator,
okay,
he wrote a little C program. You could feed it a bunch of buzzwords, and he would print out all the combinations of the buzzwords. So
it was just one of them.
Risk, Sun. Well, if you looked at the listing, one of the things that came out was Sun's processor architecture for RISC computing.
Oh, interesting.
So that's what SPARC stood for originally, Sun's processor architecture for RISC computing.
And then marketing
And
got a hold of it. Is that
and
what
then,
happened?
well, actually, Wayne Rosing realized we can't, if we're going to open the standard, how can it be open standard if Sun is in the name?
Right.
So he changed the acronym to mean scalable architecture.
Okay. And was the change accurate for the goal of the architecture though? Was it? I know later on there was embedded variants and things like that. What was it a goal from the beginning to have this to be able to scale in terms of fitting lots of different size systems?
Well, yeah, we actually thought that what scale meant is that it could scale with technology,
Okay.
not with the systems. I mean, it turns out that you're right. I mean, I try to tell people this, that the reason that SPARC lasted so long and was so successful for Sun was because it enabled us to design our own I/O interfaces. Multiprocessor coherency protocols, I/O buses, memory interfaces. The Intel ecosystem was way behind us.
Right.
So it wasn't so much the instruction set itself. Sure, it has some interesting aspects, but it enabled us the full flexibility to design a system the way we want it. Andy Bechtolsheim and Bill as architects, and then all the other people, great architects we hired, had much more freedom, to design a coherency system. I mean, I mentioned the Dragon project at Xerox PARC,
Right.
really novel. Pradeep Sindhu and Frey Long. Pradeep went later and formed Juniper. That system had a very interesting memory system. It was packet based. You would send an address out to the memory system and get your answer back later, asynchronously. So really slow from a uniprocessor perspective. Right. Oh, and by the way, what happened is, I was going to finish that story, is when I went to Sun, a few years after I was there, we announced SPARC in 87 and 88 or 89. All of a sudden, these guys from Xerox PARC were walking around our hallway. The guys I'd been working with on the Dragon project at PARC. And I go, what are you guys, Pradeep was there. And what are you guys doing here? Well, they had realized they couldn't possibly get the chipset done at PARC, so they'd come out and reached out to work with us at Sun for doing the Dragon chipset.
Wow. Which
was then called SunDragon. Mm-hmm. And the irony is that Chuck Thacker had asked me to work on the I/O chip for Dragon at Xerox PARC when I left. And when they came back to Sun, I ended up getting assigned to work on the I/O ASIC for the Dragon. So for me, it was a full circle because Xerox had decided, I think I forgot to mention this actually, before they ported the STAR software to an x86, they ported it to a Sun workstation.
Okay. So
they had decided, a SPARC workstation, so they had decided the best next step for them was to run on Sun's hardware. So I got, great, you guys adopted SPARC. I gave a talk about SPARC at Xerox. So you adopted SPARC, and now they're telling me I have to finish my work and do the I/O chip for Dragon. So it was a real closed circle. I ended up being manager of that chip, and that was an ASIC chip we did with LSI Logic. That was an amazing system. But that, in fact, I have somewhere around here I have the board. Or maybe I didn't bring it with me. No, but that it had multiple I/O cards and vertical memory DIMMs and multiple CPU chips done in the early 90s. But that's an example of how, since we had full control of our I/O interfaces, we could tailor the system. That when we were designing the Dragon system, SunDragon system, I'm like, what is this good for? There's no benchmark. When the .com era came, the Dragon came out as a SPARC Center 1000, and there was a SPARC Center 2000. When the .com era came, then there was a SPARC Center 10,000. That was the system that was used to bolster Sun during the .com era because it was just serving out web pages.
Right.
It was a coherent memory system of the highest order, but that wasn't its main purpose.
Right.
For utilization at that point.
So looking at SPARC V7 and subsequent V8, V9 as well, but specifically I guess V7 and V8 because they were both 32-bit, right? And then V9 brought 64-bit. So there were a couple of looking through the architecture manuals, there are a couple of features or design decisions that kind of stick out to me as maybe not unique, right? They take inspiration from elsewhere, but they're decisions that y'all made to include this functionality. So I'll list them off and then let you kind of choose which one you want to start with.
Okay.
But register windows we already mentioned, the branch delay slot and some of the functionality around that with different variations of instructions you could put in there, and then the alternate address space and using the address space identifiers.
Okay, well, don't get too far ahead of me.
Okay.
Let's start with the register window. So,
Okay, let's do it.
yeah, so I asked that question. I said, why are we going to stick with register windows? And, they had been clearly invented and articulated at Berkeley with the RISC 1 and 2. In fact, it was a master's student. I had forgotten about this, but it was two master's students, Halbert and Kessler, in a master's student project had actually proposed them at Berkeley. Chuck Seitz had talked about what to do with 1,000 registers, and AT&T was doing research on a lot of registers. The whole idea is that you don't need to, if you have a small number of registers and you're doing a lot of procedure calls, you have to save them right away and reload them when you come back to your procedure. So why waste all that bandwidth to the main memory or cache when you can just stick them on a little local register cache?
Right.
And have overlapping windows so that outs can become ins, and it just, it reduced the number of loads and stores. But compiler technology had advanced, certainly on the 801 project, I forgot his name, had done better optimizing compilers. How can you use a fixed number of registers like 16 and keep items there for multiple procedures at the same time? So you have to do cross-procedure register allocation, or register coloring as they called it.
Right.
And that made the compilers very complex. So here we are, a little startup company. It's hard to imagine we were a small startup company.
Right.
There were two people in the compiler group, and there was Steve Munchnick from HP. And HP had a RISC project. They were actually slightly ahead of us, called Spectrum at the time. It later became Precision. Steve was extremely closed-mouthed. He was scared about saying anything about HP's project with us. He was very, closed lip, and I think properly so. But anyways, so one day I called a meeting. So on my left was Steve Munchnick, and on my right was Dave Patterson. And I said, are we going to do Windows or not? And I turned to Steve Munchnick, and he said, well, if we're going to do cross-procedure call register coloring, right, I need two more people. And so, and I turned to Patterson and I said, well, we kind of get that reduction in load stores automatically with Windows.
Right.
So I said, okay, decision, done.
Right.
And we stuck with Windows. So that's how it happened.
There was a, I don't know if this was unique, but not all register window architectures did it this way, where you all had explicit save and restore instructions, right?
Yeah, that was a feature that we did. The original Berkeley, when you did a call, it changed the window pointer.
Right.
And a return decrement on it. So one of the OS guys, it could have been Steve Kleiman, who later became the CTO of NetApp. Steve, I think it was Steve, suggested that we decouple the two. Why not have a separate way to move the window pointer? That way you could do things like tail recursion elimination. Mm-hmm. You don't have to advance the window pointer if you don't want to. In fact, you could actually make it a traditional fixed register machine if you wanted to. Just never increment it.
Right.
Yeah, go for it. So that was really an important change that helped keep Windows going for so many decades at Sun, because when you start doing the pipelines and the very faster designs, a large 300 register file might seem pretty big to go in one cycle. And so by separating the two, and especially if the change happened in the previous instruction, or at least you could schedule the instructions, you could actually maybe start the process of reading out a row early, either by caching a whole window in one cycle, or by just charging the row early and reading it out. It's a two-step memory access, SRAM access in the chip. So by decoupling those two, that was a good idea.
And so there was a large number of registers, but they weren't infinite, right? So if you did enough procedure
Oh yeah.
calls, you'd eventually run
You
out.
had to
And
spill, you had to spill
right,
and refill, right? So if you're going up and down the stack a lot, but the programs we looked at tended to go within a range. Maybe you'd bump up here and go like this, and go down here and go like this. So it does count on not zipping down the call chain and zipping all the way back
right,
more than eight windows. But that seemed to be the behavior at the time, at least. And object-oriented languages like Smalltalk really benefited because there you couldn't allocate anything across procedures.
right,
So, for those type of environments, they were a real win. But, compiler technology by today, the RISC-V obviously is just a fixed number of registers, so people feel. In reality, the memory system ends up dominating performance anyways. Mm-hmm. So today we have first, second, third level caches, maybe fourth level caches, so that
right,
not all. And so memory has historically dominated von Neumann designs.
right,
I hate the word von Neumann, but he's a great guy, so we still use it. Computer designs.
right. So any other
you mentioned
notes?
You mentioned delay slots. So
Yeah.
that actually came from microcode. The microcode we had in the Alto and many microcoded machines had a delay slot. So, since you have to fetch, where you're going, that's going to take another cycle. Why not do something?
Right.
This is a primitive form of threading with no overhead essentially. So it seemed like a no-brainer to do delay slots. Now I added the null feature, which you could turn on a bit in the branch so that if you don't really have anything to put there, it would not do it,
right,
not execute anything. And so you could save code space and execution time in more sophisticated pipelines later. So the null bit is a way just to do a normal branch.
right.
So you get it both ways that way, and I'm sure that the future pipelines were happy with that.
Right. And so just to kind of dig into, the different options you could have for leveraging that delay slot, the most like naive thing you could do is just put a no op instruction in there, right? And
that would be a total waste. So the compiler was really tried to move something there that is independent of which way you branched.
Right. But you did have to be cognizant of, what you were moving there and how it impacted it, right? Because if you were, I think I was reading, some from literature from that time, and it was talking about, if you are doing an unconditional branch, then you could move, whatever instruction was right before the branch to after it, and that would be an optimization. If you're doing a conditional one, you could move an instruction from wherever the target was up to just after that conditional branch. And then I assume if you set the null bit, then if the branch is not taken, the instruction is annulled. Is that right?
Yep.
Okay.
Yep.
And then I also read about let me look in my notes here, the delayed control transfer instruction couple, where you have a branch and then in the delay slot you have a branch, and that gets a little bit more complex, right?
Elected to leave that undefined.
Yeah. right.
A little hole in the architecture, but the compiler just never did it, and people weren't doing hand code. So, because the problem you could define it, what would happen, but we didn't want to constrain future implementations to whatever that definition was. So we just said undefined. Don't do it.
In the instruction set, it was undefined, or in the hardware? Because I saw that in the
architecture. In the architecture, we said this will result in undefined outcomes. So don't do it. There were a few other little tiny things like that in the architecture which aren't clean, but hey, this is reality. This shit happens.
Right.
Another one was floating point underflow. Really, IEEE would prefer not, but a lot of people want to round to zero. So there was a bit that, and it may not be consistent in all implementations. All implementations may not implement it.
Right.
That kind of thing.
The other one that the other feature that I kind of read a little bit about and researched was the alternate address spaces and the address space identifiers. Was that something that was
something I did? Yeah.
Okay.
Well, putting I/O devices in the address space seemed like the most sensible thing to do. I mean, Sun had a thing where they had an I/O MMU where devices could go through that to get their virtual address. And putting devices in the address space seemed like the simplest, most straightforward thing to do. And we had a lot, because the ASI field was 8 bits, I think, you could have a lot of alternative address spaces. And we used it for all kinds of things. One of the key insights that I brought, and the OS people support it, in the definition of the SPARC architecture, was really to find something that applications and users see and don't get hung up on what the OS needs. For instance, we did not define an MMU. Our first implementation used Andy Bechtolshein's brilliant MMU design. One of the things Sun, I'll talk about that for a moment, one of the things Sun was known for in his very first Sun 1 and Sun 2 was, the Sun 2, was you put an MMU in, node cache, DRAM, you address it in 2 phases, the row address and column address. So he would send out the low order bits immediately for the row address. And then while the DRAM is accessing the row internally, he would translate the upper bits into, from a virtual number to a physical number in a table in SRAM chips. And then supply those bits for the column address.
Right.
So that meant he had a zero cost MMU. It took 0 cycles. In other words, it added no time to the memory access. And a nice hack. And we actually implemented that in the first SPARC chip. So I in addition to the architecture, I co-designed the hardware. This is a startup, right? You do more than one thing.
Right.
You do 23 hours a day. So I designed the CPU part, the processor part of the Sun 4 board. I do have a Sun 4 board here. Notice how the board's got bigger.
Right.
It occupies the entire screen. We can get into the components on it later. But in the Sun 4 board, to get a single cycle cache, who wants set associativity and TLBs and all that stuff in the way? So it's a virtually addressed cache. So the bits come right out of the integer unit, directly access the cache. In fact, I patented this idea where the bits come out unregistered, just wiggling away, and then I have a solid advanced Schottky TTL AS374 latch them and drive all the cache chips to get a single cycle cache with all these 16 plus tag chips out there. And we actually patented that idea. HP had a similar thing. They had a flow-through latch, which addressed the cache. So really, that was a huge difference from the Motorola 68020. The clock to output delay time on a 68020 is like 20 nanoseconds.
Oh, wow. Yeah.
Yeah. What happened to our...
Right.
We need a 60 nanosecond cycle time. We've already lost a third of it just getting off the chip.
Right.
And so by wiggling the chips and registering in an external beefy registered device and then driving the cache, that helped us achieve the single cycle cache and virtually addressed. Well, you still want to map multiple virtual addresses together. So we implemented Andy's MMU, and we said, if you want to address virtual addresses, if you want to map them together, they have to be equal modulo the cache size. So they have to be, the low order bits have to match the cache size. And then we'll have a tag bits on the side. We'll check the physical high order of bits to see if they're different or not. And if they're the same, we know it's the same location. So Andy's MMU saved us there too.
Right.
But I knew that I knew about TLBs, translation look-aside buffers.
Right.
We just couldn't implement it at that time. And at Xerox, when we did the Xerox STAR, the virtual to memory translation was in main memory. So if you ever wanted to do a virtual access, you had to first access the translation table, then access memory. So actually every memory access was 6 cycles, 2 slots.
Right.
That's one reason why the STAR was so slow, relatively speaking.
Right.
So, so I knew that there's no reason to formalize on a TLB or MMU. So that, and for instance, HP made the opposite decision. They formalized on the MMU management unit, and they formalized on I/O devices, and I thought that was a mistake. So that's an example of how having the system people there, they said, fine, because the kernel's going to change with every system anyways, and the
Right.
kernel's the only person that cares about this stuff. You know, it's just a mess. I/O is a mess. We're not aware of it so much now, but every possible I/O device you may ever plug into your computer back then and today, you have to have the device driver preloaded as
Right.
part of the kernel image. It's got to be gigabytes by now. Anyway, so because it's so tied to the hardware, there was no reason to put it in the instruction architecture.
That's really interesting. The idea of defining less kind of gives you more flexibility in each individual system, and that the fact that y'all had kind of this, despite being very open at multiple levels of the stack, you had a very vertically integrated team, which allowed you to understand. You could just go and grab the person in the meeting who was going to be working on the kernel driver, right, and talk to them, which really seems like that was kind of a superpower y'all had on both sides, on both the hardware and the software side.
Yeah. Like for instance, the Windows, the OS people would think about them and they go, well, they're kind of cool because I can immediately get registers I can use. Very soon after, we realized that there was a security leak there because if the kernel didn't zero them out before returning, its values were left in the register file.
Right.
We weren't thinking about security leaks. Today, everything's about security leaks.
Right.
But anyways, we had to plug that one early.
Right. Well, was there? So the SPARC architecture, like we said, evolved. It had V8 and V9. I think in V8, the multiply and divide instructions were added.
Yes.
Was there anything about kind of the evolution that you found really important in subsequent versions from that first one?
Well, I have my own view on that. I intentionally designed the instruction set encoding to be really sparse. I did not leave a lot of free bits, and I did that on purpose, knowing that it would constrict our ability to add a lot of stuff. Maybe that helped us, live with each other later on.
Right.
So, for instance, a quarter of the entire opcode space is just for the call instruction, just 2 bits. You can go anywhere in memory in one instruction. You don't have to do a procedure call, right? You can jump anywhere
Right.
With one instruction, which I thought was pretty cool. But still, it's a quarter of the address space just for going somewhere. And it was pretty sparse otherwise. One thing I did was I defined a coprocessor interface because everyone there were so many ideas, vector instructions, not a bad idea.
Right.
More graphical oriented instructions. So I said, hell, we'll just make a coprocessor space. Go do whatever coprocessor you want. And you access it just like the floating point was accessed. And that helped put to bed all that stuff. When it came time to do 64-bit, we weren't first, but it was so easy to do because the instruction set was so simple. Most things just expanded to a 64-bit format with no thinking involved at all.
Wow.
And I'll never forget later meeting when I was working at IBM Alma Research, meeting people at IBM back east, and they'd say, "You guys were so brilliant in defining the first 32-bit instruction set because it expanded to 64 bits with no work."
Right.
I'm going, we weren't
we
did not have 64 bits in mind when we
Right.
did 32. I'm not sure I had the guts to tell them that, but
Right.
because it was so simple, it was brainless to extend to 64 bits. Now, one thing that happened on V9 was Bill Joy, just a brilliant person, realized that being so familiar with the kernel, you can get in the kernel and you can get another trap and you can get another trap, and you want to be able to respond to them quickly. You don't want to have to save registers. So we added V9 added, 3 sets of extra register sets just for the kernel. So now we've even extended beyond register windows even to more. And that, those ideas happen later actually in other processors that have register sets for user kernel and virtual machines,
Right.
virtual register sets now. So we weren't thinking of virtual machines, by the way, at the time either, which problematical in some cases, like condition codes and stuff like that later. But
Right.
I wasn't around then.
Yeah. Fair enough.
But yeah.
As far as kind of like the rest of your time at Sun, I know you worked on I believe it was MAJC and Pico Java.
Yes.
Those were two things I saw in your background. I know Java obviously was very very popular at Sun. What was the how closely were hardware decisions made with Java in mind?
Well, do you know the story how Java started?
I don't.
Originally, it happened very early at Sun.
Okay.
Some of the early, there were very few hardware people at Sun. I was like the third hardware designer at Sun when I joined in '84. But one of the other hardware guys, was kind of burned out. It was easy to burn out, yeah,
Right.
working around the clock. He just went off and said, we have so many remote controls in our house, the audio, the TV, this and that. Let's design a universal remote control. So they formed their own little group, and it was called Oak at the time. And we need a language for it. Oh, we need an operating system for an operating environment for it.
Right.
So they designed both those. And later, Wayne Rosing went around and, what are you guys doing? Because he started the first Sun Labs, and what have you got here? This doesn't make any sense.
Right.
So he wanted to cancel it. But Bill Joy came in and said, oh, this is just perfect for the web now. And they renamed it Java.
Wow.
And it was Bill Joy's intervention and he realized they could all be ported. Gosling had done a great job defining the language and the runtime environment, and it was all done on the side, for a different purpose. And Bill just repurposed it, and it's just the right timing, like many things Bill did. And Java was great, but it didn't make Sun any money.
Right.
We couldn't charge per bytecode.
Right.
The marketplace had gotten more competitive. By 1998, Pentium chips were running the spec benchmark as fast as SPARCs by 98, 99. By the way, I was one of the co-founders of the spec benchmark consortium. There was this guy who had a restaurant in Campbell, and he just closed it one night, invited, MIPS, Sun, me, HP, and Apollo. And we said, we need a better benchmark. Drystone just sucks. Drystone is this old benchmark, fits in a cache, you can eliminate code. It was just horrible. So we proposed all these applications, and that became the first spec mark, integer and floating point. We were worried later because one of them was all integer multiply. Right? Oops, we didn't have it yet.
Right.
So it was
Right.
like, oh man! I said, well, that's the way it goes. Anyway, so
Right.
spec, became a nice solid foundation for evaluating all the microprocessors of that era. Where was I going with that? Oh yes, Java. So Intel was now up with us compilers. There, the techniques in the pipeline. You can do register renaming. You can do, TLB. You can just do all kinds of things to catch up with SPARC. So Bill was looking for more magic, and there were two things. One of them was Pico Java, and one was Ultra Java, which became Magic, MAJC.
Okay.
So I'm sitting in a company-wide staff meeting once. I don't know why I was there. And Bill was sitting next to me, and Ed Zander was the CEO at the time, or acting. And Bill leaned over to me and said, "How big would a chip be if we implemented Java in silicon?" And I said, "Oh, probably 3 millimeters on the side." Bill raises his hand. He goes, "We're going to do Java on silicon." I'm going, "Bill." And by that next Monday, the marketing people had already announced it.
Oh my
we
gosh.
had no design and no team. And I'm going, Jesus, this shows how desperate a company can get.
Right.
I thought it was a dumb idea. I ended up giving a talk about it at Microprocessor Forum one year. It's just because I wanted to talk at Microprocessor Forum. And they formed a team that started working on it, and it was eventually canceled. In fact, my neighbor ended up being a manager on it. I now know. But I thought it was a dumb idea. I had Bill try to defend it, but It was just one idea to try to. The other idea we had, which I think was better, is I held an offsite at Asilomar here in Monterey,
Okay.
and I invited the graphics guy, Michael Deering, just a brilliant graphics person, his son. He wanted to, by the way, the technique thought was important then is to render a triangle fully with complete illumination, based on the scene, and but most chips couldn't do that at the time.
Right.
Jensen and two guys, I forgot their name now, at Sun, they were trying to do that with Michael's advice, and they left and formed this little company called NVIDIA.
Right.
Jensen, by the way, used to be our LSI field rep from LSI Logic.
Okay.
And now he's CEO of NVIDIA.
Right, of course.
Amazing person. But the three of them were sitting around one day and said, one of us has to be CEO. And so Jensen said, okay, I'll do that.
Yeah.
Really nice, amazing man, built himself up from the bootstraps coming here as an immigrant. But they were kicked out of Sun, basically, because it was just too hard to do that kind of graphics chip. So anyways, I invited Michael Deary, and I said, what can we add? What can we do to bring Sun back in with a hardware story that makes us look like a leader again? So we had lots of walks on the beach, and we realized we could add a graphics pipeline to the CPU. It seemed like there to be just enough transistors now to do that. And since we had Java, we didn't need to make it SPARC. We could make any new instruction set we wanted.
Oh, right,
back to
right.
the drawing board, full open. And so we did that. Mark Tremblay was the architect, and he designed a whole new instruction set. No register windows.
What was it named?
Well, at that time it was Ultra Java, the internal
Okay.
code name, but that became Magic. That
Okay.
became
I see.
and it also had threading. If you're going to go out to memory, let's do something else under that. Same ideas, from delayed branches and stuff, but now to a much greater extent. Same Alto ideas, like,
Right.
while you're waiting for memory, go execute another stream. So I think it was the first multi-threaded hardware chip out there, I think.
Wow.
But it is tied to the Java story and and graphics. Well, we soon realized we couldn't fit the entire graphics pipeline on the chip. We could do all the triangle rendering, all the floating point, floating point, and, AI algorithms. Anybody? We
Right.
could do all that on the chip, and we'd do the back end rendering on a separate chip. But we needed to find clients, and so I would fly to Japan and visit with Sega, and they would go, Java. They're hand coding primitive machines, and they're doing patches where you don't render the triangle with the lighting. You just know, well, with this kind of scene, it's going to look like this, and you just fill it in.
Okay.
All shortcut methods. Today,
Right.
graphics are so realistic, it's just pathetic. But back then, it was a hack.
Right.
And so they thought no, we don't need this. We couldn't find a user, and the only user ended up being a graphics accelerator at Sun.
Right.
So, $200 million just to speed up a graphics accelerator. So that, in some sense, that project was not a success. But it hired a big team of people.
Mm-hmm.
Speaking of non-successes, at Sun, when we did, we talked about SPARC. Well, I next became head of the logic design, architecture, logic design, and CAD group for Ultrasparc. This was in the early 90s. And Viking was the name of the chip before us. That was our first. People go, SPARC is such a good idea. Where is the full custom chip? So we hired Jim Slager and somebody else from Intel who had done the 386.
Mm-hmm.
They came and hired a team. They wanted to do bi-CMOS, which is bipolar, and CMOS. And we thought, ugh. And a very complex pipeline. Well, that project, unfortunately, fell like 2 years behind, and Sun was now behind the market. Luckily, there was a recession right then, so the sales guy could still sell our current stuff, amazingly.
Right.
So Viking came out late. The Sun Dragon was based on Viking.
Okay.
But it came out late. So during that time it was late, Anand Agarwal, who had been really the spirit leader behind our relationship with Fujitsu, started an ECL design project, ECL SPARC, working with BIT, and that was a lot of work.
Mm.
How to design it in ECL with the whole board, and it was like we had two camps. We had Slager doing CMOS and Anat doing Eckel. SPARC was scalable, right? So maybe Eckel was a good place for SPARC, but we fell behind in CMOS. And so one day Andy Bechtolsheim said, I've just had it with this. We need to be like Intel. We need to have two CMOS teams leapfrogging each other. Intel had Santa Clara and Oregon, each working concurrently. So you got a chip, like pipeline, you got to chip out every year.
Right.
So we stopped the Eckel project. Well, actually, no, before we did that, the guys were like, well, let's try gallium arsenide. So, and not actually put me in charge of the gallium arsenide program. Seymour Cree's looking at gallium arsenide. We worked with Vitesse. I would come in to work on Mondays and go, let's go for it. And by Friday, this is hopeless. Right. Gallium arsenide technology, it turned out that the P-channel devices were slower than the N-channel devices, and there was no memory. Vitesse was excited to maybe do a processor, but they were too small of a company. That's the point. Andy came in and said, I've had it with these two teams. So,
right.
Guys, you guys you're Echo gallium arsenide guys, you're going to do a CMOS processor. So that became what we call Spitfire. And now Slager's all pissed off because now there's a competing team. But now we had the problem, we're behind in the market. How do we hire a team to catch up? And we had to hire 200 people in the course of, 6 months. And we would interview 6 people a day on Fridays, review 20 resumes and decide who to hire. And we did find people who wanted to help save Sun. Les Cohen, who did the i860 at Intel, the first 1-MIP chip. He came as the lead architect of Spitfire. I worked with him. Anat was in charge of the whole project, and we pulled it off. We pulled off 167 megahertz, 5.3 million transistor chip on schedule, and brought Sun back up with a reasonable performance and a great systems, as the system people designed. So that chip, Spitfire was called Ultrasparc 1, and then Ultrasparc 2, and then Ultrasparc 3, and then some other SPARC chips fueled Sun in the 90s. But by the end of the 90s, like I said, Intel, with their Pentium chips, had caught up with us in performance. And there were some, I was not at Sun anymore, but they did some amazing Sun chips through the early 2000s up until an Oracle. Larry Ellison bought them. Scott knew Larry Ellison from years ago, and they did some amazing chips while they were there. And I mean, the only reason, the Oracle products had kind of the same performance whether it was an Intel chip or a SPARC chip. So Larry finally threw in the towel.
Right.
Fundamentally, I think Patterson has come around to this, that the fundamental difference between RISC and CISC back then was that CISC machines were microcoded. And RISC machines were not. And so, that didn't matter anymore by the time year 2000 came around. The IBM PowerPC has become the most complex instruction set in the world. There are literally hundreds of instructions, every instruction known to mankind.
Right.
Every instruction known to mankind. Even ones you can't even imagine. There's decimal floating point. All the decimal instructions came back. There are sophisticated instructions for virtual machine handling, remarkable main memory models. The complex, transistors are free. Metal and the size of the chip are important.
Right.
But the instruction set size has become a non-issue now in running these things.
Right.
The times really changed.
Right. Well, kind of rounding out your time at Sun there. I know you went on to do a number of other very interesting things that we might cover in a follow-up episode. But I did want to hear and talk a little bit about what you're up to today at the Computer History Museum. You talked about the history of Ethernet, so I'll kind of let you take that whichever direction you think is best there.
Okay. Well, let me definitely talk about the Computer History Museum. So I always had an interest in history. In the late 90s, after I was discouraged, I worked on a project called Genie for a while at Sun before I left. And I started volunteering at the Computer History Museum. And it was like the Valhalla of these great computers, right? Craze and everything all over the place. And
right.
I got to know the staff. And in 2003, I started working on a restoration and demo project for a DEC PDP-1. And that was DEC's first computer in the early 60s, 18-bit machine. It was used a lot in universities. In fact, Space War was written on it at MIT, and Nolan Bushnell was wandering around as a grad kid not knowing what to do and saw Space War, formed Atari.
Yeah.
From that experience. PDP-1, so it was in universities. And he used to say, by the way, that women would walk up to him and thank him for their marriage. And he would say, what? Well, because in all the bars, there were these Atari machines, and women are known to be good at playing games with and so they would always win and get to know that. So a lot of marriages were, Nolan was proud of that. So while we were working on the PDP-1 restoration, Mike Chaponis, who was the spearheading that, he heard there was an IBM 1401 available in Europe, and he said, would anyone like to lead a team to restore it? And I had just joined IBM Alma Research Center, and I didn't know anything about IBM computers. I cut my teeth on DEC and SDS computers, and I was not interested in business machines.
Right.
To be honest. And so I just joined IBM, and I said, sure, I'll do that. and then I said, what's an IBM 1401? And then I look online, I go, holy shit.
Right.
5-ton, 12 kilowatt computer from the early 1960s, late 1950s. And so the next question was, how am I going to get a team to restore that? So someone said, there's a group of retired IBMers in the Bay Area. So I put an ad in the IBM retirement newsletter, IBM 1401 needs help. 2 weeks later, about a dozen retired IBMers who had worked on these machines, proudly worked on these machines in the field, came in and said, we'll help you get it to work again.
Wow.
So after 2 years, 3 years, 4 years, it started to start working. Germanium transistors, which are not the most reliable transistors in the world. Solid state, IBM had switched to solid state in 1958 from tube computers. You would think that solid state, would be pretty hardy. Well, I soon learned that they had packaged the transistors in TO5 cans that had iron in them. And guess what happens when you put iron in a moist environment in Germany for 20 years
Right.
in a car garage? So I became worried. We had just purchased 10,000 rusted transistors because we were finding 2 to 3 bad transistors every week. And one night I get a call on my cell phone. This guy in Connecticut calls and says, my father has a 1401 in his basement. I said, what? And are you interested? And I said, sure. And, it had been operated up until 1995. Yeah.
Wow.
The internet existed in 1995.
Right.
And his customers were Westchester County golf courses or something. And he converted his home into a little data processing center and fell in love with the machine and never stopped.
Wow.
Had a little water damage, but we brought it in and a rainy day, of course. And the day it arrived in our lab at the Computer History Museum, which is, by the way, SGI's old headquarter building, the server room of SGI's headquarter building. At Sun, we were really proud to help put SGI out of business because graphics wasn't enough to get them going, but servers were. It arrived the day it arrived in the lab. The German system started to work. It's like, if I don't shape up, I'm going to ship out. And by having 2, we can make sure at least 1 is working when we do live demos. We have trained docents that give live demos of the systems, and maybe at least 1 of them is working on any given day. There are 500,000 discrete components in each one. It was the world's most popular computer in the mid-1960s, before the IBM 360. There were over 14,000 installed worldwide. It was it quickly became, and people you would never imagine loved it because it was their first computer. Alan Kay, the author of Smalltalk, that's his favorite computer.
Wow.
He didn't run business applications. He wrote an OS and a metacompiler for it. And,
Right.
but it was a computer, and kids think it's a T-Rex dinosaur. And we speak of it as a time machine. When you walk in that room and smell, especially people from that era, a mainframe from that era, it has the magnetic tape drives, it has the mechanical card reader, it has the mechanical printer, the chain printer, 90 inches per second, hammers, 132 hammers that fire. It's like a cross, a student said, between a machine gun and a typewriter. And it looks like a T-Rex dinosaur, and people love it. I mean, they love seeing something so real. So it's been great fun for 20 years. While I was still at IBM, one day a week, the CEO of IBM came to visit one time, Ginny, and I gave her the tour, and I said, I work at IBM, and I was too young when this computer came out. I didn't know it back then.
Right.
She looks at me and goes, "How do you find time to be here?" I said, "Oh, pink slip in the mail tomorrow."
Yeah, right.
I said, "Well, at IBM, you guys have a big community service component. So you guys can support this kind of thing." So
that's awesome. That's really cool.
So come by the Computers Museum if you want to see a live demo. Saturday mornings at 11 and 1 p.m. or Wednesday afternoons at 3. They have trained docents who give the demos.
Absolutely. Well, next time I'm out that way, I'm definitely gonna have to make it. You also mentioned you're working on this history of the Ethernet. Tell me a little bit about that and kind of what the goal is there and current state maybe.
Yeah, I am. Yeah, that's a really exciting project. I worked on I did that Ethernet, those 2 Ethernet adapters for Bob Metcalf at Xerox, and then I went to Sun Microsystems. So Andy was really tuned into the importance of Ethernet. He made sure it was on all of the cards. And I mean, he had been at Xerox PARC as a no-fee consultant, but I was there working on the Dandelion. He was across the street. I didn't know it, building his own workstation based on a 68000 and an amazing small multi-bus Ethernet card he did. So it was important, but I was not part of that. But a friend of mine at Xerox, a dear friend of mine who's passed away, who did the analog part, people contacted me and said they want to know more about how Ethernet came out of Xerox. And I said, it's boring. But when I looked at it, I could see it wasn't well written up technically. Right. So I started talking to people and expanded. So I've decided to do a complete technical history of the Ethernet, starting from AloaNet. It's inspiration by AloaNet. I found the AloaNet designers.
Oh, wow.
I've done an oral history. It's now online with them. So from AloaNet in Hawaii, which was the inspiration for Bob Metcalf to do Ethernet, through his work with David Boggs and others at Xerox PARC, a little bit of our work, with the Xerox STAR, and then all the subsequent initial cards that came out, and then standardization in the IEEE 802. That's a lot. Right. It turns out, I dare not get to the modern era because that would take 10 more volumes. But right. I've talked to 140 participants so far. Wow. 140, and lots of interesting stories. And I'll be visiting with Bob Metcalf next month, actually, at his home in Austin. So wow. It's I guess it really left an impression for me, and seeing how it played out, because it was a fierce battle out there, and its standardization, it got standardized at the same time as token ring and token bus. And in a sense but because it was so simple and it was so straightforward for people to build interfaces for it, and the protocol layers took care of problems at the hardware layer, fundamentally it won. Token ring, you have to wait for your turn. Good thing that doesn't work today, right? You can't make a telephone call until a red light comes on. That would be bad. Because it allowed packets to be lost, so-called collisions in the original Ethernet. Originally on the cable, somebody's transmitting here and somebody's transmitting here, and they might listen, but they're too far apart. They're not going to hear it in time, so they're going to collide, and the packets are going to be wiped out. Right. That scared people. Right. But PARC's Universal Packet Format, later TCP, ARPANET was unreliable too, so would come back and retransmit the lost packets. And the AloaNet retransmitted lost packets, so they never had any collisions probably. But that scared people, but that was so important because when it made the transition to switches, Ethernet switches, initially, the first Ethernet switches didn't have enough bandwidth all ports in to all ports out, even assuming it's equally distributed. Right. So if a port got overloaded, the microcode firmware could just go, just throw some packets away. Right. So, because it allowed, it almost promoted, in a way, the destruction of packets, which would be fixed at a higher level. And Metcalfe really cared about reliability, but in the right way.
Right.
It led to its total dominance of all communication. I like to say that it's possible all human to human, machine to machine communication goes through an Ethernet.
Right.
Or an Ethernet derivative like Wi-Fi at some point.
Wow. That's a really interesting design insight of, being unreliable in a way at the lower level allows for a more reliable, complete system because you're deferring to the upper levels.
Yeah, you're not trying to
such a
solve
consistent
every
way.
problem at that low level, which
Right.
people always tend to want to do. They want to be good engineers. They want to,
Right.
like Chuck Thacker thought it was. He was a brilliant designer of the Alto and his work he did at DEC SRC, but he never thought it was a good idea. He said, no, the customer deserves your ability to deliver all the packets.
Right. Right.
And I worked at a fiber channel company at Brocade. I was director of hardware there for a while. And there we actually did deliver every packet in order, but it was more of a constrained environment and smaller, kind of a micro net instead of a local area net.
Right. Interesting.
Yeah.
Well, how will folks be able to once the history of the Ethernet is complete or in a state where you're comfortable with it? How will folks be able to get eyes on it?
Well, I should put it on the web, but it'll be a book, but with pictures because people don't have time to read books. So I'll have a lot of pictures and diagrams. And if someone wants, they'll usually go to the section they're familiar with. So
right.
But it's going to be another year probably.
Gotcha. Awesome.
Yeah.
Well, I'm sure that'll be really exciting when it comes out. I'll definitely.
I'm worried that only the people who read it will be the people I've talked to, but yeah, it's good to know that someone else might be interested.
Well, I'll definitely want a copy of it. So okay. I think that sounds incredible.
Okay. Well, thank you.
Absolutely. Well, I think that's probably can wrap us up for today. But like I said, I think there's even more we could cover. So if sometime in the future you're willing to come back, I'd love to have you back on.
Oh, yeah, that'd be fantastic.
Awesome. All right. Well, thanks, Robert, and have a good rest of your week.
Oh, thank you for having me on your show and your podcast.
Absolutely.